All right. So, if you missed yesterday, last class period, we went through all these properties, definitions, postulates, and theorems, and you need these notes. So here we go. So if you're in the boat where you were absent, didn't take them, whatever, here we go. It's gonna be long, but I'll try to go quick. All right. So the whole point of this sheet is to give us some information. So if you kind of consider that we've tried using diagrams and pictures in the past to prove stuff, it's never really worked out. Whether we're measuring, tracing, using compass constructions, transformations, or just looking at a picture and trying to reason out what has to be true, like I said, just never really worked out. So in this final iteration of proving things are congruent, we're going to use a picture to extract some known information, a relationship, and use that to actually prove that things are congruent or other pieces depending on the situation. So the purpose of giving you the names on the left and showing you what the structure looks like, and then the relationship is to emphasize that relation or that kind of connection. Excuse me. So what you're going to see here in the structure column is probably going to be some kind of picture, but over to the right is going to be what you can tell from the picture. And so when you're looking in this case at the reflexive property, you're going to have a visual key about what you're going to see, and then what you can tell because of that picture. And these are exact, so please take these all as facts. Let's do it. So reflexive property. Let's talk about a structure. So reflexive property talks about a shared side. So let's say I have this triangle and I have this triangle right here. So kind of maybe in a parallelogram shape. If I label this triangle, or these triangles, excuse me, A, B, C, D, we'll note that B, D in both triangles are going to be shared. If it's shared, that means we're talking about them being congruent. So the reflexive property tells us that BD is congruent to BD. And again, there's nothing mind-blowing about this. It is just a property, but it does give us an opportunity to go from a picture to a workable statement. In this case, congruent statement. BD is the same as itself. That may or may not help with something else. Like it's like maybe a triangle congruency postulate or property, or maybe I'm just trying to prove like two objects are kind of similar. Whatever have you, now you have the reflexive property. Definition of congruency. This one's also very straightforward. Definition of congruency states that if I have these two triangles, let's kind of orient them this way. Let's call them triangle ABC and then DEF. That if they're congruent, I know that these sides are the same, these are the same, and these are the same. But I also know that angles are going to be congruent as well. It's been messy. Okay. So that's all it's saying. Like, so if I see triangles that have all matching information, I can tell the triangle ABC is congruent to triangle DEF. All right. Transitive property. This one is very algebraic in its application. So let's say we have a triangle here, and then we have another triangle here, and so we have another triangle here. And let's say I'm further told that these two sides are congruent, and then completely independently of that idea, I know these are congruent. And just so I can stop using pronouns, let's call this triangle ABC, and then DEF, GHI. Okay? Well, if you look at the congruency markers, I have purple that's congruent to pink, and pink that's congruent to pink. I'm sorry, purple that's congruent to purple, pink that's congruent to pink. Another way to write that would be AB is congruent to DE. And then I also know independently that DE is congruent to GH. So if you notice that there's a shared side on both of them, both the AB and the DE are both congruent with D. I'm sorry, AB and the GH are both congruent to DE separately. So the transitive property allows me to cut out that middleman and jump directly from AB to GH. Okay? And so, like I said, very algebraic operation, but you're just skipping over the middle shared part. All right, let's talk substitution. This one is very, very algebraic. So if you remember, if you recall an equation kind of like this, let's say you have x plus 2y equals 4, and then you're told later on that x is equal to 3. I bet everyone in here would put the 3 in place of the x. Okay. Put it in place of the x. Whoa. 700. And let's continue your solving. So if you do something like this is called substitution because you are putting the 3 in place of something they know is equivalent to. In terms of geometry, it's probably going to be more commonly seen kind of in this way, with measurement of, let's say, angle ABC plus a measurement of angle DEF equals 200. And then you later on find out that the measurement of angle DEF equals 71 degrees. Well, again, we see this repeated DEF um, in both of the statements. So substitution allows me to write in hmm, and if you look here, instead of writing angle DEF, I'll write in the actual value, which would be 71, and that's going to be equal to 200. Okay? And so the thing again I want you to pay attention to is that we replace 71 with the thing that told us how to convert 71 to an angle, which is a statement, and that's substitution. Definition of supplementary complementary. Let's focus on the picture first. So supplementary complementary makes sense most on a line. So let's draw one going straight up at a perpendicular angle, right angle. Let's take the other one and split it up into a couple parts. So let's call this angle 1, this angle 2, this angle 3. So what, definition of supplementary tell us is if we look purely at angle 2 and angle 3, those are supplementary. Complementary. Jesus. And because they're complementary, I'm allowed to write this statement. The measure of angle 2 plus the measure of angle 3 equals 90 degrees. Okay. So along those same tokens, if I look at angle 1, angle 2, and angle 3 together, those are what we call supplementary. And that's because if I take the measure of angle 1 plus the measure of angle 2 plus measure of angle 3, that should equal 180 degrees. So with the end, complementary refers to 90, supplementary refers to 180 degrees. Okay, let's talk about these 4 conditions. Corresponding angles, biconditional postulate. Don't get too hung up on the name. Postulate's a fact. We know what angles are. Corresponding angles are angles that are in the same location, and you'll see what I mean here in a moment. Biconditional just means there are 2 conditions, and you can start with either one, and it leads you to the final result going through the one you didn't use. Now, all 4 of these next ones all have to do with 2 parallel lines being cut by a transversal. Okay? And that's going to lead us into some information about the same 2 lines and a third line. Excuse me. Okay. And so we're also going to label these, let's say, A and B for the lines. I'm going to leave the right one unmarked for now because I think it's better that we see it as clean as possible. And these are going to be the same exact structure is going to be used for the next 4. So I'm just going to go ahead and set that up now. I'm going to go ahead and copy and paste the same structure in. This structure is actually a wildly powerful one in geometry because it allows us to transfer something about side lengths, in this case parallelism, to some level angles. Now, we've always suspected those 2 things are actually linked, but these particular theorems actually prove they're linked, which is a step in the right direction. Okay, so let's talk about this first one. So we're starting with 2 lines being cut by a transversal. So our lines are A and B, our transversal is this pink guy. And we got to talk about corresponding angles. Well, corresponding angles are angles that are in the same location. So if I choose, let's say, this to be my corresponding angle, I'm going to call it A. A. There we go. All right. So if I want the corresponding angle to angle A, I want the one in the same relative location. So if I look at the cluster of angles that A is attached to, I see A is in the bottom right. Actually, let's not call it A. Let's call it angle 1. And then the corresponding pair should also be in the bottom right, but a different line location. So that's angle 2. Now these turn out to be congruent. So if your lines are parallel, these angle pairings turn out to be congruent. So let's go ahead and write that. So if A is parallel to B, then angle 1 is congruent to angle 2. Now, if you think for a little bit, and when I finish speaking, pause the video so you can ponder this. My curiosity is that I call this a biconditional statement. And so by biconditional statement, I said there were two conditions, and it didn't matter which one you start with. So go ahead and predict if you want to what's going to come next. And hopefully you'll see that it's just a reversing of these two items. So if angle 1 is congruent to angle 2, then A is going to be parallel to B. So again, this is why we call it a biconditional statement. It's two conditions. You can start either end. One here and one there. And so like all we're going to do for the next three is just point out like other angle pair relationships. This one was corresponding angles. So I picked out a pair of corresponding angles. Of course, I'd also mention there are other choices, like here and here could be chosen. That's alternate interior. I can choose here and here as well. I can choose this guy and that guy. Now, of course, I'm not going to put those all in the diagram, simply because it's going to be a little too much space, and of course, there's another pair there. There's going to be not enough space to show all that and just get really messed up. So just know I'm showing you one possible example, not all the possible examples. All right. So here we got to find alternate interior angles. So alternate is going to be either side of the pink line. Interior means inside the two, A and B. And so the lines we're looking for, the angles we're looking for, have to be inside and alternating. So these two should work, and I'll call these 1 as 2 as well. Of course, there's another set here and here. Again, I'm not going to actually draw the arc markings. We're just talking about one thing at a time. Okay, so let's go ahead and write our statement. So I'm going to write it a little differently this time. Pay close attention. I'm going to write angle 1 is congruent to angle 2 if and only if A is parallel to B. Okay. The if and only if language means the same thing as writing the statement twice and reversing it. It just happens so often that they give it a special name. Alternate exterior angles. Okay, so alternate exterior angles will be either side of the pink but outside the green lines. So there's an example of alternate exterior. Again, it's not going to be the inside because that's alternate interior. That's the one we just covered. So I'm going to write this one in a very kind of a unique way as well. So I'm going to write angle 1 is congruent to angle 2. IFF angles, lines are parallel. A is parallel to B. IFF is just a shortcut for the terminology if and only if. So it's totally okay if you want to use that. Okay. So moving on, the next set, last set, excuse me, actually has a typo. So let's change alternate to consecutive. Okay, so consecutive interior, well, interior means inside the lines. Consecutive must mean in this case same side of the line. Now, the more sharp among you might realize that I've actually used different tick marks for these, is because these do not turn out to be congruent. These turn out to be supplementary. So I can say that angle 1, angle 2 are supplementary. If and only if A is parallel to B. And again, you might notice I switched notation again. There are actually 4 ways to say a biconditional statement. I can use arrows. I can use the term IFF, which is if and only if. I can write the whole thing out as if and only if, or I could write 2 statements. I'm not going to really force you to memorize that. It's just something good to know. All right, so it's not a structure, something you could write here. At least I'm not going to use this format, but it is worth it to take some time to make sure that you have the ordering right in your triangles. So what I'm going to do now and encourage you to do is to draw on just 4 triangles. They do not have to be the same size or anything or same type. Just draw on 4 triangles. Okay, and then let's mark some information. So in the top one, I'm going to mark 3 sides. Over here, I'm going to mark 2 sides and an angle. I'm sorry, 2 angles and a side. Here, I'll do 2 angles and a side as well. And here will be 2 sides and an angle. Okay, so certainly none of these are congruent. But what these could hopefully help you see is that the order here does matter of the information you're trying to prove. So like for the first one, if you're trying to prove side-side-side congruency, order is not going to matter there because they're all just sides. You can only place them one way. But if you look at the two on the right, the order here does matter. On the top, I would say I have an angle that has a side in between it and another angle. So this guy would be an ASA, triangle congruency proof. Whereas the one on the bottom, which also has two angles in the side, the side's actually outside the angle. Sorry, not trapped by the angles. And so this one would be angle, angle, side. Just like the name implies, the side is outside the two angles, and the one above it, the side is in between the two angles. So on the same kind of token, this one will be just be side, angle, side, and there are no other variants that work for that one. All right, the home stretch. Let's talk about linear pair postulate. Linear pair postulate. Linear means line. Pair means at least a couple. And so we have a line cut into a couple different angles. And so what the linear pair postulate demands is that we tell angle 1 and angle 2 that they are let down. Oh, let me. We can say angle 1 and angle 2 are supplementary. Okay, let's talk vertical angle theorem. So vertical angles are the result of an intersection. So we have, let's say angle 1 here and angle 2 here. This demands that angle 1 is actually congruent to angle 2. That's vertical angle theorem. Triangle sum theorem, well, let's draw a triangle. Let's talk about the three angles in a triangle. Let's label them 1, 2, and 3. Triangle sum theorem tells us something we already know, that if I take the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, that's going to equal 180 degrees. Okay, base angles biconditional theorem. Base angles biconditional theorem is something that applies only to trapezoids. So that's a terrible trapezoid. Let's try that again. So trapezoids mean that you have two sides are congruent. Now base angles, the base of a triangle is actually a side that has a special relationship with the other sides of the triangle. It's not necessarily always the bottom as you were probably taught. So in this case, the red is actually the base. There's two angles on it, one at the top, one at the bottom. I'm going to label them 1 and 2. So base angles biconditional theorem says, well, if I have this isosceles triangle. So I have this isosceles triangle that tells me that these two angles are congruent. Oops. Okay, so angle 1 is congruent to angle 2, so let's go ahead and mark that. And let's go ahead and write it. So this is a biconditional theorem, so this is like an if and only if statement. Just for our own use, I'm going to call this side up here side A, and this is side B. And so this theorem states that A is parallel to B if and only if angle 1 is congruent to angle 2. And being biconditional, you can start at either side, meaning that if you have congruent angles, you have an isosceles triangle. If you have an isosceles triangle, you have congruent angles. Okay, CPCTC. Let's talk about this guy. CPCTC stands for congruent parts of congruent triangles are congruent. So I'll say it again a little slower, that congruent parts of congruent triangles are congruent. So if you simmer on that for a second, you realize RIDI actually has something that explains this. This is nothing more than just a definition of congruency. Okay, but it does have some kind of practical application, and you will see it like an ACT test, a standardized test. So that alone tells us, well, we have to at least make sure we're familiar with the terminology CPCTC. But here's how it could play out. So let's say you have this triangle, and you have this other triangle here. And you know that certain information is already true. Let's say these angles are congruent, this side is congruent to this side, and that side on the bottom is congruent to that side on the bottom. So if you consider that, like right now, you realize that these are congruent because of side angle side, CPCTC justifies you in saying all the other pieces are too. So again, if you think about CPCTC, congruent parts of congruent triangles are congruent, we're saying, well, even though we only proved only part of the information, we have side angle side in this case, CPCTC allows us to say, well, since the triangles are congruent, these angles should be the same, along with these angles, along with this side. Okay, so you can think of CPCTC as just a justification for saying, well, once I've proven just enough information, everything else comes along now for free. All right, last few ones. Now, depending on the packet you were handed, there are two versions that were handed out. Yours might say definition of congruent, or yours also might say definition of equality. They kind of mean the same thing, so go ahead and write the other word in that you don't already have. Here's how this kind of plays out. So let's say I have like this rectangle. Let's call it ABCD. And because you know it's a rectangle, you also know that these two sides are congruent. So in other words, AB is congruent to CD. Definition of equality, property of equality, definition of congruent, property of congruence. Remember, it's congruent, not congruence or congruency. If you know things are going to be structurally the same, structurally identical, you can say that their measurements are going to be equal. And notice a couple things. I dropped the symbol above the heads of the letters. That's because we're no longer dealing with a structure. And also notice that it's no longer congruent, but it's equal. So you can make a little note here that this refers to the measurement. In other words, the numbers. No, I didn't leave this on the day. Did I leave? No, 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 no. I might have left a blue bag in there though. Yeah, I'll be right there. I just need to finish making this video. Oh no, it's no problem. It'll be weird for the students, but that's okay. So it refers to measurement number. Well, over here, this is purely structural. Oh, right. Definition of perpendicular. So let's draw in some perpendicular lines here. So let's say I have this line that comes across. We'll call it AB. And let's say we have CD crossing it at a 90-degree angle. And so we have this angle, actually have four, but I'm just going to focus on one. So we can say that AB is perpendicular to CD. So if that's true, we know that angle 1 is a right angle. Okay. Now you also might have an extra one here. Mine doesn't, because like I said, there are two different versions that are floating out there. So angle 1 is a right angle. So let's write in the definition of right angle. Okay, and all this says that is if angle 1 is right, that means the measurement of angle 1 equals 90 degrees. Okay. So like the final word is here, notice you have a couple empty boxes. That implies that we can add to this list as we need to. And that's something I want you to really think about, is that just because it's not on this list doesn't mean that it doesn't exist out there somewhere in geometry. So even in the homework you're working on or will be working on soon, I think something is mentioned as a midpoint. And midpoints, by definition, can break something up into two congruent halves, which means you can add that to this list. You can say, well, okay, I do know the definition of midpoint. This is what it means. This is what it looks like. You have the power to do that. You have the permission to do that. Oh, it looks like my picture dropped. Sorry about that. I don't know how long ago that happened. But anyway, the video is done anyway. So just know that you have the power to do that. So that's that. So that's your notes. You have homework and you have some practice you need to do. So if you've missed this before, now you have your notes. You can actually do it. Thank you.